Well, hello there, and welcome to 6.2.3 on Public Key Cryptography. We're continuing our lesson in informatics on security, how we can securely transmit data across the interweb. Previously, we talked about symmetric key crypto systems. In your crypto venture, that's what you learned about. Crypto systems where the same key is used to encrypt and decrypt. You can probably see how that's a little bit less secure than what we're going to talk about today and what a public key crypto system is. An individual in a public key crypto system creates two different keys, a public key, which is shared with everyone, and then a private key, which only that person keeps and only that person is able to use. As we go throughout our examples with cryptography in this lesson, we're going to talk about Alice and Bob a little bit. We don't talk about them as much. We don't go as in-depth into this lesson as the book does. But if you want to know who Alice and Bob are, you can watch this guy. He's actually a college professor, even though he doesn't look like it. Basically, they're just two fictional characters that we use to simulate these situations. So, for example, Bob has created a pair of keys. Here's how a public key cryptography system would work. Alice uses the public key, because that's the only one she has access to send an encrypted message to Bob. So her message is, "Hello, Bob." But what Bob sees is this big mess of things. That message gets to Bob. In order to decrypt it, Bob uses his private key, and he decrypts the message to say, "Hello, Bob." That's basically what we're doing in public key cryptography. Two major applications for this. Secret messages, where a bunch of people are sending things to one person. We'll show a couple examples in a second. And then digital signatures, where one person is sending something out to many people. We'll show an example of that as well. For secret messages, two basic applications would be, if you think about a credit or some sort of company online, some online shopping, where a bunch of people are all sending their different credit card information all to the same company. That would be one example of secret messages. Another example might be all of the U.S. embassies across the world. I don't know, there's dozens of them. They all send them back home to the U.S., so a bunch of different embassies sending different information all coming to one spot. That would be an example of securely sending things by secret messages. The other example, the other application with digital signatures, where one person's sending out to many people to make sure that you can be sure that it's this person that you're getting this thing from. Digital signatures come into play. Now, if you got this email, you might want to be a little bit sketched out, because sending it to 1,200 people and saying something like "you are special" is usually not a very authentic message. But generally, you're not going to see messages like that, because digital signatures help to block that thing from going out. All right, the public key crypto system that we're going to specifically look at is called the RSA public key crypto system. We're not going to talk really about how it was made, but these guys, Rivest, Shamir, and Adelman, are the ones who created it. One of the most significant developments in the history of cryptography. The reason I included that is because RSA is named after their last names, Rivest, Shamir, and Adelman. So that's where the RSA comes from. The keys for the RSA public key crypto system are numbers constructed using large prime numbers. The larger those prime numbers, the more difficult to crack the system. And modular arithmetic, which we've been learning for the past couple lessons. All right, so we're going to go through two examples, and we didn't do everything in 6.2.2, I think it was, so I'm going to give you a little bit of extra information than you would normally be given, but you're still going to have to do some of this new modular arithmetic that you've learned to help you encrypt and decrypt these things. So you should see page 469. You should have your books open to page 469. There's a whole using the RSA crypto system procedure there listed for you. We're going to use these specific numbers to try to encrypt the message fully and then decrypt it so that you understand the basics of how this system works. All right, so on page 469, you're going to see we've already, in constructing the keys, we've already done step 1. We've computed our we've chosen our two prime numbers. That's going to be 3 and 11. For step 2, we're going to say n equals 3 times 11, so n equals 33. You might want to write that down because eventually we're going to go to a calculator and you're going to not see my writing on this screen. It says to compute R. I don't think, in fact, I know we're not going to end up using R because R is only used to compute E and D, and I've given those to us because we didn't talk about multiplicative inverses, which you see in steps 4 and 5. So then, after we would have all these numbers created, we would jump down to step 6 and where it says publish E and N in a public directory. So E and N, 3 and 33, would be the public key that everybody would have access to. And then step 7 says keep D secret along with P and Q. So D, P, and Q are going to be the numbers that we keep, that we know what they are. That's going to be the private key that we're going to use to decrypt anything that's sent in to us. All right, so at this point, if you've got these numbers written down, we have enough information to start encrypting our message. So step 1 in encrypt says convert the plain text message to numbers. Basically, we're going to use those 0 through 26 numbers that correspond to these letters. So F, I believe, is, I've got it written down somewhere. I think it's 6. 6, 12, 5, 5 is our flee word. Okay? Step 2 says raise each number to the power E. Our E is 3, so we're going to take 6 cubed. I'm not going to show you the online calculator yet. I think you can follow this much on your own. 6 cubed is 216. 12 cubed, 1,728. 5 cubed, 125 and 125. And step 3 of encrypt says reduce each number mod n. The resulting number is called the ciphertext number. Mod n, we're in mod 33 then. We want to figure out what's the remainder of each of these things when we divide by 33. Okay, here's where I'm going to, got to make sure I've got these numbers written down, which I think I do. Or maybe I should write them down. 216, 1728, 125. All right, I'm going to show you an online calculator so that you completely understand what's going on here. All right, our first number is 216. We want to take 216 divided by the mod that we're in. 216 divided by 33. That gives me, I take 33 into 216 6 full times. Okay, with a remainder of something. So I want to take 6 times 33. And now I'm going to compare 198 to 216. The difference between 198 and 216 is 18. So my reduction in mod 33 for 216 is 18 mod 33. So my F now I've converted all the way to 18 because that was my remainder. Okay, so 18 should be your first thing that you write down for your encryption. The next number was 1728. We're going to divide that by 33. That goes into, or 33 goes into that 52 times. So we're going to take 52 times 33. And that leaves us with a remainder of 12 between 1716 and 1728. So 12 is our remainder there. That would be our L encryption. We'll do the same thing with both of our 125s. 125 divided by 33 goes in there 3 full times. 3 times 33 is 99. 99 has a remainder of 26 in mod 33. So 26 would be our final 2 letters there. So our encryption for the word flee, E for encryption, would be 18, 12, 26, 26. Now obviously this is more powerful than our symmetric key crypto systems that we worked with in our crypto venture, because you can't just simply shift these to get to flee. Yes, you might know that these 2 letters are going to be the same, and in a very simple message like this that might help you, but in the long run, this is going to be a much more powerful crypto system than what we were working with earlier. All right, now we want to decrypt it to practice the opposite operation, so to speak. So if you go back to page 469, the 3 steps for decrypting. We're going to raise each ciphertext number to the power of D. So I need to take each of these things to the 7th power. And then we're going to reduce each of those things mod n and see what they convert back to. Okay, so you should have those numbers written down. We're going to go back to our calculator. And our first number is 18. We have to take 18 to the 7th power. 18, where's my exponent on this thing? 18. Only took me about half an hour to find where that was. But anyways, 18 we would do to the 7th power, and that didn't do 18. Let's try that again. 18 to the 7th power. You're going to see we get an answer that has scientific notation. That's not going to help us out at all. So we're going to need to use one of the things that I briefly showed you in, I think, 622, where we're not going to take 18 to the 7th, but we need something where we can see the whole number. So I'm going to take 18 to the, let's try 5th power, and I can see that whole number. Now I need to remember that I've still got 18 squared left over, because I haven't used all 7 powers of 18. But I'm going to reduce this in the mod that I'm supposed to do, and that's mod n again. So I'm going to reduce this mod 33. That goes in there 57,259 times. Take that times 33. And my difference between this number and this number is 21. So I'm currently at 21. But you have to remember I still have that 18 squared left over. So I'm going to take 21 times 18 squared. Now I have accounted for all 7 of my 18s. Now I'm going to divide this by 33 and figure out what my remainder is. 206 times 33. Looks like I have a remainder of 6. So my decrypted number is going to be 6. And that's a good thing because we know it should have been 6 because that's what we started out with. So 6 we're going to convert back to the F. And we've got one of our 4 letters. All right, now we're going to do it with our second one. We have to do 12. 12 to the D power. 12 to the 7th. Again, that's too big on our calculator. We need to start a little smaller. So I'll start 12 to the 5th. That number I can see, I probably could have done 12 to the 6th. So maybe just because we did 5th last time, let's show you 6th this time. 12 to the 6th looks like this. Remember, I still have 1 12 left over. I'm going to divide by 33. That goes in there 90,484 times. Difference between these two numbers is 12. So I'm going to take 12 times the 112 that I still have left over and reduce that in mod 33. Goes in there 4 times 33. With a remainder of 12. That's a good thing, because my second letter should have been a 12 for L. So now I've converted the second letter to an L. Let's show you the third and fourth letters. They're both 26. I'm going to take 26 to the 7th. That's going to be too big. How about we do 26 to the 4th? And reduce that mod 33. 13847. Looks like my remainder was between this number and this number, 25. So I'm going to take 25 times the 3 26s I haven't used yet. And reduce that, mod 33. 13315. 5 times 33. Looks like my remainder there is 5. So both my last numbers are 5, which is a good thing because those both convert back to E's. All right, I'm going to leave this problem. This is just like the homework problem that you'll see it for the assignment. So if you want to come on during classroom or during my office hours at all, and we can go through this problem, I want to have you, as much as possible, try to go through that homework problem by yourself. So we'll leave this one in case we need an extra example that you want to go through with me. Otherwise, here's your assignment. Number 5 is working with that public key cryptography. 25 is just a review, solving, I think, 3 different equations of varying difficulty.